Welcome to the Air-Sea Fluxus from Space webinar series. Today we have Clément Ubelmann and Jinbo Wang, who are going to talk about near-inertial surface currents, challenges and opportunities in the context of Odyssey. And I think they want to emphasize that they are hosting this, not presenting, and they want to make sure that we have open discussion throughout the presentation and at the end. So please feel free to raise your hand and pop in.
Yes.
Take it away.
Yeah, that's the idea. I think we have 25-ish slides. So the idea is also to have some time for discussion and questions. As an introduction, we'll start with these three figures that illustrate the difference between the geostrophic component that is observed today by deriving the altimetry at a synoptic scale, and the total surface current that is fairly different. And by the way, this is why there is so much excitement, I think, about Odyssey mission. Because today we do not observe total surface current at synoptic scale. We do have drifters that are extremely useful. We'll never have enough drifters, of course, to be able to map globally the total surface current at all scales. But they are really nice. It's that they give a flavor of what the surface current is. And there's an illustration here. When we look at the drifter trajectory, the Lagrangian trajectory, we see this really nice loop that are happening right now here on the screen. That are obviously not explained by the geostrophic field derived from altimetry, but the result of inertial motions that are very clear at the bottom time series derived from the drifter position, superimposed with the geostrophic velocity for Aviso. So there's a lot of stuff on top of this geostrophic velocity, and Odyssey would observe the sum of all these different components. Now I can, okay, now I can switch. Now let's switch to a numerical model data. You can see, by the way, that this series in black look fairly similar in statistics to the drifter derived velocities. Jinbo will talk more later on the validation of the current scenes from numerical simulation that we use. But there's an illustration here because that is important to make. It's going to be a Doppler, a spaceborne measurement. So constrained with with orbital constraint, the temporal resolution can be infinite. Although for Odyssey, it's a very thanks to the large swath, is very favorable. Still in the 20 to 60 latitude band. If we look at the frequency of revisits, it's longer than the inverse of the Nyquist frequency of near-inertial oscillation, the dominant frequency, the Coriolis frequency. So obviously, if we were to just low pass the data, this illustration is from another mission concept, but just take it here really as an illustration on top of a cherry-picked example where the NIOS event is very strong. When you low pass this, obviously, you cannot reconstruct NIOs, and you can guess the observations of the high frequencies to lower frequencies. That's well known. And what we want to show today, the main message is that first, with specific mapping methods, the Odyssey-like observation allow good separation and reconstruction of the main different components, including the inertial band at high frequencies. On top of that, a good knowledge of the wind forcing, also even the wind forcing that we have today, typically from Era 5, also explains a large part of the NIOs. And Jinbo will go over this, showing really some opportunities for NIO Odyssey in this subject. Then a third point, which I think should be considered as a bonus, but if we think that in the future we'll have this wind measurement, this future Doppler total current, and also altimetry, which we hope is still going to exist, that would really bring unique opportunities to disentangle different components and better understand dynamical interaction. I will add that there's a lot of research ongoing right now on the interaction between NIOs and mesoscales, and this really brings great opportunities on top of the first 2 points for the mission. First, I'll go over method one. I'll go quickly over the main principles and results. That's a lot of these materials are already published, and you can go have a look for further details. The basic principle is to have here a pure statistical mapping, so without wind knowledge for now, based on multivariate mapping involving oscillatory kernel. I'll give illustration of that. We've implemented that in previous concept, and now with the Odyssey simulator, so for the Odyssey concept. And the results is thanks to the very large swaths and good time revisits of Odyssey, up to 70% of NIOs that can be reconstructed in simulations, with an overall 70 to 90% in the 100-500 kilometer band for the total current. So not only we better reconstruct NIO, but we can also, by avoiding aliasing, well reconstruct the whole range of spatial scales of the surface current. So here, just an illustration of just showing with hand the principle of this mapping is to use oscillatory kernels that are fit on the actual covariance of observed total surface current. And from this covariance, we build a kernel that can match them and use this for mapping, along with other components, in particular for mesoscales. That I'm not gonna detail here. It's everything is shown is published in the paper. And if we take again this first example that I showed earlier with this obvious aliasing and that we had with the blue curve, now when we use this multi-component mapping, we have this red curve for the heterotrophic current. With the ability to reconstruct the high frequencies of NIOs. And also, I'll go quickly on that, but when we, the use of these oscillatory kernels also allows to better reconstruct the whole range of scales, with a good addition when we also use altimetry, but it's not necessary. We've implemented recently with this is work by Solène Jousset at CLS that implemented this the method to Odyssey observations in the LLC surface current scenes that features very realistic NIOs, by the way, and Jinbo will come back on that. And after a few adjustments, some results came, and here as an illustration that shows again in black the ground truth considered in the LLC simulation of the total surface current. Also, these little rectangles here in red and black represents the time revisits of Odyssey, typically twice a day. And in blue here is the reconstruction with the NIO mods and the reconstruction of the total surface current. You can see on the animation here at the bottom the ground truth velocity on the bottom left compared with the reconstruction here. I don't know if you see my pointer, by the way. That could be useful for later.
Yeah, we see the pointer.
Yeah, you do see. So okay, great. So yeah, you see that high frequencies are well resolved, and also quite small scales in these high frequency, small spatial scales are quite well resolved here in the mapping. These are more quantitative diagnostics showing on the top left in black the rotary spectrum, the clockwise part of the rotary spectrum, because we see the inertial peak here, of the LLC UV spectrum, clockwise spectrum, sorry, with in blue the same rotary spectrum of the reconstructed current. So you can see that in terms of energy around the inertial peaks, we're quite good, and also at lower time frequencies. This, well, energy is good, but phase could already be wrong. So we're always also looking at a score that look at the phase by looking at the spectrum of the difference ratio with the spectrum of the ground truth, to be able to have a percentage as a function of scale of how much of the signal is well represented. And you can see here that if in scheme we were about like 50%, now thanks to the better sampling, we reach up to 70–80% of construction if in NIOs. And also, if you compare with the purple curve that does not use the oscillatory mode, you can see the difference, and also the difference at lower frequency, showing that by better reconstructing NIOs, we also help the ensemble of the whole range of scales of the total surface current. Also, if we look in the spatial scale dimension, is very interesting. We also basically the main message is if we look at the different reconstruction scores on the right, is that first, even without NIO cares, actually the mesoscale between 100 kilometers and 500 kilometers are already quite well reconstructed. It's quite fair scores. And when we add this NIO modes, these mesoscales are even better resolved, and especially at very large scales where NIO dominate. Here, altimetry is with standard constellation is shown as just for comparison, but here in this experiment, the synergy is not exploited, and we know there's a lot of possible synergy. I think I will leave the floor to Jinbo now, right?
Yeah, Jinbo, do you want to go ahead?
Oh, I forgot I muted myself. So this is the another independent study after Clément's. What we used is just a least square problem based on linearized SLAM model. And we used the 5 mooring observations: hourly surface velocity, and wind is from ERA5, hourly winds. So we use these observations and simulated Odyssey sampling, both winds and surface currents. Obviously, it is undersampled, right? Twice a day, approximately in mid-latitude. And then we use the existing simulated Odyssey sample, integrate a SLAM model forward over 10-day period, and try to optimize by adjusting initial velocity, mixture depth, and damping coefficient R. 3 parameters, 4 parameters if you split U and V. So by adjusting that and integrate this SLAM model fitting to the Odyssey simulated Odyssey observations plus the noise, then we can. The question is, can we use this SLAM model reconstruct what's missing between the Odyssey samples? So the conclusion is that in the low eddy energy, for example, the northwest of Pacific, where station Papa is, in reconstructing this highly coherent NIO is very, very easy. We test a different method, but all of them actually give us pretty good result. And on the contrary, if we move into the Kuroshio extension region, we also have a mooring provided by NOAA PML there in KEO. Also record hourly surface velocity. So we use that too. Then in that region, as you can imagine, the high frequency variability contributed from the sub-mesoscale mask out the NIO signal. So if you subsample it, then the reconstruction is less. It's not completely wrong, we'll show that, but it's less accurate. But we're gonna argue that in this region, NIO is not a dominant signal in the velocity. The most dominant signal is the mesoscale and sub-mesoscale. And also NIO has a larger spatial scale relative to the eddies. So that brings to the third point. Can you go back, Clément?
Oh, sorry. Yeah.
Yeah, 2D swath give us the ability to do spatial operation. You can do derivative, derive the vorticity, and vorticity has less for.
You need to advance the slide.
Sorry, we're not.
Right now we're on the presentation of method 2 slide. That's not number with the reference on it, right? That's
Eric,
not...
which slide are you seeing right now?
Me, I'm seeing
whatever you're talking about is the same slide that Jinbo just covered.
Yes, I think it is item C in the list. So
yeah, results item C.
Yes.
So I just quickly go through the conclusion first. The slide C is slide C result point C. I want to make is the wide swath you can do spatial operation. NIO and mesoscale, some mesoscale eddies has different spatial characteristics. So in addition to the time series analysis based on mooring, using numerical simulation, for example, the most recent coupled MRT-GSM actually shows that further spatial operation can mitigate the NIO problem. So the conclusion of our paper, or the point D, is that NIO signal is more of an opportunity for Odyssey than thread. So this is the simplest model we can use in the adjustings. People have more sophisticated data simulation model, should do much better job. The next slide, Clément.
Yeah.
So this is the 5 mooring we took a look, and as you can see, the 20 to 60 degrees is where the potential alias happens. So we focus on these 2 typical moorings: Kyo region, crucial extension region, and station papa. This on the right hand side, this diagram, this figure shows the low frequency, presumably the mean circulation, mesoscale, and some mesoscale eddies on the horizontal axis, and vertical axis is band pass filtered NIO with units of meter per second. The 1-to-1 ratio is the red line, right? So majority of the region among 5 moorings have more low frequency variability than NIO. The exception is the station papa has more near-inertial oscillation than mean circulation eddies. Okay, so this set the stage that these 2 moorings, station papa and the crucial extension region, has 2 different signal content. Next, Clément. Again, this is the simplest approach that we use least square fit Odyssey UNV to a SLAM model. The SLAM model does not have background share. It's just the simplest one. And we adjust, and can you press next? We adjust the free parameter. Oh, it doesn't show there.
There's not the animation, right?
Yeah, we adjust the initial velocity, mixture depth, and damping coefficient. Okay, next. This is the result. Just go quickly. This is the station papa result. I did 2 scenarios. On the left-hand side is a scenario with a narrower swath. It's not relevant right now because we already fixed a better orbit. But you can see that with even sampling frequency less than twice a day, at the station papa case, we can still reconstruct the NIO because NIO is the dominant signal. The truth is the gray curve. I'm not sure you can point that to the gray curve, Clément. That's right. And the Odyssey sample is the blue dots.
Yeah.
And predicted based on the Odyssey observations are the red. And the filtered NIO truth from the gray line is the green line. They are basically on top of each other. The RMS difference over 1 year period is 2 centimeters per second. Based on the reconstruction, we can also calculate the wind input, which is on the bottom panel on the right-hand side. The SLAT model is orange. True NIO wind power, wind energy is the blue over 1 year period. So the next one. We also did another case, completely independent analysis method for the station papa. This is work done by Han. Basically, we use a forward simulation forced by ERA5 winds on a forced LSC for 540, 16-degree MRTGSM. There's no data simulation, just forward simulation. But if we use the real wind, actually we can reproduce the NIO signal pretty well in these the two panels. One is U, another is V. The model is the blue, and the observations from station papa is orange. And the most impressive part is the phase match between the two. Of course, in the reality, we do have a little bit of a mesoscale and mean circulation. We cannot match exactly, but the level of the ability of the forward forced ocean simulation that can reproduce the station papa near-inertial oscillation, that give us hope that a little bit of data simulation will help match the Odyssey observations and the reality. So we did not do full-blown MRTGSM data simulation, but this is a demonstration that the dynamics in the real ocean is captured by the low resolution models. Next, Clément. This is the more challenging region, crucial extension. So if we go through the lines, let's say focus on panel B. So the Odyssey observation is simulated in orange dots, and the gray line is high frequency part of the observations, and the filtered NIO is the black solid line, and the SLAT model fit is the green line. This is the blue line. It's hard to distinguish the blue from the green. Green is simply harmonic analysis, and the blue line is on top of the black line. But this is a better case in panel B. Panel D is less accurate, but still the phase is still matching the observations if you compare the blue and the black. So this is less accurate using SLAT model. The RMS difference becomes 5 centimeters per second, but the scale of the prediction scale of the SLAT model still persists in this case. Now we only have time series at one point. We cannot do spatial filter separating the signal. So the hypothesis is that if we have wide swath, we have more spatial information, we can do much better than just a simple 1.1 time series based SLAT model fitting. The next one. So by the way, all these results can be found in our recent paper. So it doesn't show. This is actually from Brian Arbic and Shen. Compared to the most recent couple, MRTGSM and Drifter over near-inertial oscillation band. The upper panel is undrugged, and the middle panel is drugged and Drifter, and the third panel is the ratio. So if you focus on MRTGSM, which is the LSC for 2160, Brian, I know you are there. Correct me if I'm wrong, or maybe you can jump and explain this. The green line is a forced MRTGSM. It does not have, if we do latitude band average, it does not have enough NIO compared to the red line, right? That's the Drifter based. But if we coupled MRTGSM with the hemisphere model, and that's the blue line. It becomes much better. At this point, according to Brian and Shen, that it's hard to see that coupled MRTGCM is weaker than reality because there are a lot of uncertainties in the drifter analysis too. So the take-home message from here is that the new coupled MRTGCM actually reproduce NIO to a level that we can trust, to the accuracy of order of magnitude matching the reality.
I think that's a good summary. I mean, maybe Shen could jump in a little bit. It is not exactly apples to apples because the model sampled in an Eulerian way, and of course the drifters are Lagrangian. So that might explain some of the differences, but obviously the coupling makes a big difference. Big improvement over the older ocean-only model.
Yeah,
and also for undropped drifter, there is an influence of a wind slippage in the drifters that is not in the model.
Yeah, and Shen.
Yeah, no, as Brian said, it's not exactly apple to apples for the comparison of the two models, but for MIT GCM LLC 4320, the forcing is 6 hourly, and we've known for a very long time that it is not enough to simulate near inertial energy in the ocean. So we definitely need higher frequency forcing of ocean model only, and then perhaps also couple models to reach the level of energy that is actually captured by the drifters.
Yeah, I guess another thing is the drifters are sampled over, I think, 30 years. Shen knows better than me. And this is a particular model year. So that's another non-apples to apples point that I suppose might make some difference if there's interannual variability in near inertial waves. Although this is a global average, so I don't know how much that matters.
Yeah, so thanks, Brian, Shen. I want to use this to establish the credibility of the new coupled simulation in representing the reality of the NIO, right? So the next slide, Clément, is the spectrum analysis based on the wide swath 2D spectrum lumping into the 1D, and we also, because we have hourly data from model, we bandpass to get the near inertial oscillation, which is orange line. Sub-inertial is the blue line. This simply based on the frequency analysis, and then we did a spatial wave number spectrum. So you can see that below 500 kilometers, basically the eddies dominate over NIO, almost order of magnitude. So this is based on the crucial extension region. If we go to next, these characteristics let us do spatial operation like this, right? On the left-hand side is the kinetic energy wave number frequency spectrum. The inertial band is marked there, and we can see there a huge energy, but the energy mostly focused on the large spatial scale. If we use this velocity and calculate the relative vorticity, and then do another wave number frequency spectrum analysis, which is on the right-hand side, most of the near inertial oscillation, near inertial band is gone because most of them are in a larger scale. So if we think about the slant model, if we want to add a nonlinear term, and we can simply use Odyssey observations and derive reliable background shear from eddies without without temporal analysis. So this is another point that I want to make, that wide swath has a huge advantage over just time series analysis existing in our studies. We have not delved into that, how to take advantage of spatial wide swath in the NIO, but that's definitely a benefit and advantage. Next one. This is another one. This is away from the slant model study. This is just an illustration of what existing right now. On the bottom panel, we have the velocity from the keel mooring which is the blue line. If we subsample simulate using Odyssey sampling frequency, which is the orange line, and also added 10 centimeter per second noise onto it. And the green line is the interpolated Oscar onto the mooring position. Now, Oscar product, surface velocity. As you can see that the existing velocity product missed a lot of events that actually is important. For example, in the U prime T prime eddy flux calculation, if you miss three eddy events pointed by these red lines, you will miss a lot of the true values there. So the three peaks, if we look at the sea surface temperature satellite images, actually they are corresponding to a big eddy events. The first, the blue star is mark the mooring position. The SST on the top left, you can see that there's a big meander from crucial extension. In the middle, there's another meander really past the mooring. And the third event is the eddy retrieving. So it will capture by Odyssey, but it does not capture by the altimeter-based surface velocity product. Next. That's yours.
I can take the floor. Yeah, following on one Jinbo just showed a few slides ago on the reconstruction from the wind. He mentioned that, well, the phase match was impressive, but there are still some differences, especially also at more spatial scales between the reconstructed NIOs and from the slab model and the reality. And actually, I just want to point Bjorn Kallis and Kohn et al.'s work, a very recent work that show that, well, they are doing very active research in understanding the NIOs and mesoscale interactions. And as we can see here on this figure from their very recent paper, we can see that they can reproduce the modulation of the amplitudes of the NIOs here due to the presence of mesoscales. And actually, these are quite large mesoscales already seen by altimetry, and that could even be seen without altimetry with Odyssey alone with very low pass filtering. So I just want to point that this is really, I think, now a bonus, but that gives a lot of perspectives because we could further understand and reproduce the mechanics of interaction between NIOs and the mesoscales, especially when we think that, well, we should have high resolution, hopefully altimetry as well. And by using all these different data, that's a lot of perspectives. Just very quickly, I looked at the MIT GCM signal. I will skip on this, just a very technical way to filter the NIO with respect to the rest of the total surface current. But this is what we get, and I found that quite interesting. So on the top left here is the total surface current magnitude in LLC. Okay, that's the magnitude of the current, just to really clearly show the presence of these eddy rings in the Gulf Stream and the main path. And on the right is the extracted NIO signal from the hourly data. That's here one component here on the right, but at the bottom is the amplitude of the NIO, and at the bottom right is the phase. And what I found interesting is, like, we clearly see very similar amplitude modulation, for instance, on the bottom left, than what we had here from a very from a reduced model by Hugh and Bergeloun, now studied by Kohn et al. 2023. You can see here, for instance, this amplitude modulation look fairly like the one we see in LLC. So I think that's really great perspective and can have a lot of confidence that these this research field should be very promising to understand NIO and mesoscales and even resolve the whole system of interaction in presence of ODC observation between the wind, the observed wind by ODC, the observed total surface current, and also the low frequency eddies that are seen either by ODC and also altimetry. So that's my take on this. Well, I'm sure Bjorn would have also many other details to add on that. But I'm sure.
Just want to emphasize
perspectives.
Couple simulation.
Sorry.
This is the couple simulation.
Yes, yes, of course. The one that seems to be very realistic with respect to what we observe from the drifter. Referring to the blue curve of the figures a few slides ago. Also interestingly, we see some modulation of the phase when there's a big NIO event. I think it's going to be soon on my screen. No, well, not this one, but the following one going from the southwest, which is now. Yeah. There's a atmospheric front, and as you see this amplitude, which is interesting is if you look at this big ring eddy here, the phase is initially the same as it's triggered by this atmospheric front going through. But then in the end of the event, the phase offsets, probably because of variations of the relative vorticity in this big eddy. But this is all explained with these simplified models currently studied. So I found that interesting. I think, I can leave you with main messages here on the very good scores of reconstruction with ODC-like observations and the different methods to handle the NIOs, even without wind forcing, and then with wind forcing and very simple slab models. And third point, all the perspectives we have in merging that all together.
That's the end, Clément.
Yeah, so that's the end. Now that can take questions and go back on some results.
Yeah, well, thank you. Let's open it up for discussion.
Yeah.
I see Eric Desaro has his hand up.
Yeah, for those of us who aren't NASA nerds, can you briefly describe what the sampling of Odyssey is going to be?
I think it's, well, there's kind of, I think this animation here gives an idea. We can see the width of the swath. So you see the ascending path, and then 12 hours later, the descending path, basically. On here, here the animation is only 24 hours, but actually the orbit is not one day exact repeat. So the local position on the swath differs days to days, which is, by the way, also a great advantage for handling tides, but that's not today's subject.
And what's the swath width?
2,000
1,600 kilometers.
Yeah.
Yeah, so it's an order of magnitude wider than SWAT.
Yeah.
More than that. Other questions? Shen has his hand up.
Hi. Hey, Jinbo. Thank you very much for giving us an overview of your paper. I think you showed a scatter plot of near-inertial energy versus low-frequency energy at a selection of moorings in the ocean. And I think you have a figure, this one. What is your overall conclusion here? What is the conclusion from that analysis?
This is, the main conclusion, well, this is just 5 points, right? It's not a global analysis. The NIO, I want to use this plot to highlight the KEO region and the station papa region, the distinction in the partition between NIO and background mesoscale, submesoscale mean circulation. And that the signal content give us two different scenarios in terms of the NIO reconstructability. The station papa has more NIO signal. If you even subsample daily, you can still reconstruct the near-inertial oscillation pretty well because that's dominant signal. In the KEO region, the mean, the low frequency dominate over station papa. If you do not remove the mesoscale, which we can, but we cannot based on the Morin time series. But in reality, we can remove the mesoscale. If we cannot remove mesoscale based on the signal analysis of one time series, it's harder to construct NIO because NIO is not a dominant signal in there, right? So we actually have a better chance to think about wide swath scenario and separate mesoscale, remove it from time series, and then fitting a SLAM model will be much easier.
So, if you think it's useful, we can expand this graph. We can just take the maps that we created with Brian in our 2022 paper, and we can give you a complete scatter plot from MIT GCM, HiCom, and from the drifters, because we did the same, right? We estimated the energy for the NIO band and for the low frequency. And even if I think you use different, limits of integration for the spectrum, we can provide you a complete scatter plot so that you can determine this type of regime everywhere in the ocean.
Yeah, I think that would be helpful to tell the story, right? Different region have a different capability of dealing with the NIO.
Yeah.
A PDF of the global distribution.
Yeah, we can give you maps. We can do everything from the results. I mean, it's available from the paper. Anybody can do it. But that gives you a global view from the drifters and from the two different models.
Yeah. Good suggestion.
Brian has his hand up.
Yeah, I just wanted to quickly say that, on a longer term, I think data assimilative HiCom could also be useful for this. We're not really working on that in the context of NIOs right now, but right now we are working on it in the context of predictability of internal tide SSH. Some of you who were at the SWAT meeting saw that. We can basically map internal tides on a wiggle by wiggle basis on a global scale with the same level of accuracy as Ed Zarin's empirical model. So I don't have great intuition about whether near inertial velocities are easier or harder than internal tide SSH. But if we can do internal tide SSH, we could probably at least give a try to just get, phase accurate near inertial oscillations in an operational model. There's problems with the Navy output, like releasing it publicly is difficult. And the way they do data assimilation is a bit noisy, but again, on long time scales, we can probably fix those sort of problems. So I'm just saying, if we can do internal tide SSH, near inertial velocity is another possibility, maybe.
Yeah. So that's, Brian, I think that's great suggestion. That's probably we should do, right? The using data simulation to reconstruct this signal. That's actually our entry point 3 years ago on this problem. Try to use MIT GCM, but we did not do the 40R, but we just forced a 1/6 degree forward model. What do we find? Exactly what I explained, that in eddy energy high region, because of the background eddy is not in the forward simulation, and we could not get NIO correct phase in this forward run. But instead, if there's no strong background eddies being main circulation, they simply force the model can capture that. And if you add the data simulation on top of it, especially put the eddies in the right place, I think that will be the slam dunk solution.
And probably also add the forcing in the control vector, because if the forcing is prescribed, then we know it's not, and since it's very clearly related to the NIO response directly, I think it's probably in the data simulation important to include the forcing in the control vector. But this technical, yes, these techniques exist, of course.
Sarah, and
Great. Ernesto has his hand up.
Yeah, we don't hear.
Ernesto, we
Yeah.
can't hear you.
Maybe
We
we'll
see
need
you
Ernesto to
unmuted.
put a comment in the chat.
We can take other questions.
Well, while
about
we're
the
sorting that
vector.
out, can I ask a question?
Yeah.
I guess I'm struck that I think Shen in his earlier work looked at a whole family of variants of slab models. And I'm wondering if the case you're looking at would be an opportunity to revisit that family of slab model variations to assess what gave the best response, or whether there were spatial variations or differences. So maybe that's a broad question for a lot of people.
Yes, it's a great suggestion, Sarah. I would love to be able to do it. So with Jonathan Lilly, we actually unified that theory. And so we realized that there's only like 2 families of like transfer function. The only thing is that for a slab layer model, you have one free parameter, which is going to be, I believe, the depth of that slab layer. The problem with the series of transfer functions that I looked at in the past, you have more free parameters, up to 3, including, the seminal like vertical viscosity, as well as the boundary layer depth. And so these are free parameters that are hard to, pick whenever you try to run, this type of simulation. So that's a difficulty that I see in trying these things.
And then Shane, could we consider like to go to a 3-layer models to get a bit more parameters, but not too much, or is that?
Yeah, I think some people have tried, multiple layers, but you seem to be increasing the number of free parameters that you're going to have if you want to run this, more physically based models, right? So I think the slab layer model works very well in some instances, but it's not physically based. Like the instantaneous transfer of momentum throughout the water column. So if you try to go from physically based model, then you have more, free parameters, and you need to be able to pick them. And it's a bit tricky to decide which they should be. That's my view on it.
But they could be controlled with Odyssey-like observation, we could imagine.
So Ernesto has put his question in the chat. Can NIO characterization be used as a crude estimate of mixed layer depth? This would help tie surface fields to deeper circulation.
Yeah, we actually talk about that at the JPL with Alex, Tony, and Hector Patrice. Because mixed layer depth is a control parameter, that's something we can reconstruct from by looking at Odyssey observations. We have not done it, but theoretically, it should be doable.
Yeah, like for instance, I think in the backups, I have a slide that show that, is this here or not? Oh, no, I'm sorry, I don't have it. But basically, we looked at the transfer function when looking at the wind and the current shown by the drifters, and we could see that the transfer function was fairly different in winter and summer. That shows that clearly when we observe surface current and wind, I think we can infer some of the properties of the mixed layer depth. by just looking at the inertia of the response.
Right. Sarah, there are some chats in the chat box, and also
Yeah,
Eric.
there's a lot in the chat. So going back to the beginning, Shen asked for the, I guess for the mooring estimates that Jinbo showed, which wind product did you use to force the slab model? Or maybe that was earlier even.
This earlier, yes. The
Yeah.
mooring produced the surface velocity and wind.
Oh, sorry.
It was at Station Papa. It wasn't clear which wind you used, but maybe you used from the book.
No, that's after, right? No, that's no. If you want to look at the time series or from Station Papa, that was.
Yeah, this one, I think.
This.
So did you use hourly winds?
I did use hourly wind, yes.
Okay. So you were thinking of, extrapolating that to use like a reanalysis product to do it globally, and then suggest that then you could simulate properly the near inertial oscillations if we had hourly winds? Is that your implication?
Yeah, we do have a wind, but we need the ground truth to fit to. I think if we do globally, we have to rely on the simulation. Yeah. So Eric has a new comment, Sarah. He has to leave. There are several intermediate models better than SLAB model and simpler than full simulation that could be useful for this is something that we should talk, Eric, at some point.
Yeah, since I actually haven't left yet, I'd be two comments. I'd be really surprised if you couldn't get quite a lot about mixed layer depth from this sort of model. I mean, from this sort of data. I mean, the response is inversely proportional to the mixed layer depth. So you really ought to be able to extract it with a little bit of effort. And the other thing I said here is that the main weakness of a slab model is the damping makes the frequency lower than F when the frequency should be higher F, and that the first order effect of propagation is to change the phase, not the amplitude. And so there's probably some intermediate type models that would allow you to do that. That would be better for doing simple extraction of the inertial.
Yeah, and I think in this model that fixes the problem.
Yes, that's exactly what I'm referring to. The first order term has got the I there, the second term, right? And so the question is, can you approximate that term as well as in an assimilation in a simple assimilation model?
Yeah,
that would be better. That would be anyway. That's all I had to say, and I gotta go.
Thanks, Eric. Quickly, the initial velocity was a free parameter, both U and V, that will adjust the phase. Okay, I think Eric left.
Yeah. Other comments? There's also some comment in the chat about possibilities for using HiCom, and it's maybe worth just reading that.
Yeah.
Anything else on anybody's mind?
Sarah, Ernesto has another comment in the chat. Lack of mixer was identified in the C-star review as a major weakness in relating surface to deeper field. It probably will come up for Odyssey.
Okay, yeah, that's a good point.
So yeah, through looking at NIO, and we could, as Eric pointed out, we could potentially look into the mixer depth reconstruction.
Right, and then the width of the swath helps with the NIO, so it's something where Odyssey has maybe a lot of potential.
Yeah, so of course there are small scale NIO, but I think the dominant energy is at large scale.
Yeah. And smaller scales are understandable. That's the thing also. There are small scales, but with great chance to handle them with such models.
But Sarah, in the end, I hope that, the group can have some comments that in this along this line, what could be the top of priority, or do we have enough materials to go forward to address some potential comments?
Yeah, so maybe it's worth explaining what people are thinking about, the sort of broader context that Odyssey is under review at the moment. In a couple weeks, we will get a list of potential major weaknesses from the NASA reviewers. And so in anticipation of that, everybody is racking their brains to think about everything that could possibly come up and how we would be prepared to respond to any potential major weaknesses that are identified. So this is an exercise in thinking about everything that could possibly go wrong. And so thinking about how we address the near-inertial oscillation came up as one of the things we should try and make sure we were on top of everything we already know. And I think the point has been that if it could be identified as a weakness and it could be identified as a strength, and it's a question of us packaging what we know as accurately as possible and explaining the opportunities. So Tony says he thinks we have enough NIO related material to address a potential question. And I think that's true. But if we get stuck, we'll reach out to everybody we know for help, because this has to be a community effort.
Yeah.
So
Thanks.
before we wrap up, any further questions or comments? If not, we will finish up. Next week, we have a harmony-related talk by Owen O'Driscoll, I think.
Thanks, sir.
So
Thanks, everybody.
I'm going to stop recording.
Thanks everyone.